things to do. All right, so I had asked you to open up to page 3, which is where we took notes yesterday on internal and external energy. What I would like you to do for the next like 3 or 4 minutes is on the bottom of the page. Actually, you know what? Did we really skip insulation, or did I just skip it? Or did we not get anywhere here? I see a whole bunch of people writing. All right. This must not be your packet. Let's try this again. Oh, okay. All right. Let's start there then. So we did the reading. We highlighted the answers, right? All right. I'm getting confused with my classes. Yes, sir. No, not usually. All right, so we were here yesterday. So we'll just start just kind of reminding us what we did. We read that reading on page 2, and then we needed to put those actual words into, or the actual stuff we read into our notes. So we're going to start with internal energy. What was that, guys? Yeah, that was energy from inside the earth. And there were 2 causes, which we talked about yesterday, which is radioactive decay. So that half-life stuff we did about a month ago, that also gives off heat. And then the Big Bang, hopefully that at least sounds familiar to you, is how the earth and the universe was formed. And it also is a big explosion. It was a big bang. It gave off a lot of heat. Now we're talking about external energy. Where does external energy come from? That is energy from the sun. So if you don't have this, go ahead and add this to page 3's notes. So external energy is energy from the sun. Then I had asked you in the reading, and you might need to flip back to the reading to see what you highlighted. I had asked you to find 3 things that affect how much external energy reaches Earth. Did you find those ones? Flip back to the reading and see what you highlighted yesterday. What was the first one? The first one is the angle of insolation. So here's what that officially means. It just means the position of the sun in the sky. Meaning, is the sun directly over your head? Is it down near the ground? Hopefully you know that when the sun is directly over your head, it's going to feel hotter than when the sun is down by the ground. If you don't, we will bring that up next week.
I have a question. So for the Big Bang Theory.
Yep, we'll talk about that in chapter 9.
What chapter?
7.5. What was another thing that affects how much energy we get from the sun? So one was how high the sun is in the sky. Go back to the reading. Did you highlight another thing that affects how much energy we receive from the sun? You got one, Drake?
Is it amount of insulation and the length of time the sun is visible in the sky?
Yes, that's officially called the duration of insolation. Just like Drake said, it's how long the sun is in the sky. If the sun is only out for 9 hours, like it is here in the winter, we don't get as much energy from the sun like when it's out for 14.5 hours during the summer. So we'll be able to get more energy the longer it's out. And flip back in the reading. Somebody new, find that third reason or third thing that controls how much energy reaches us from the sun. Find it down there, Brooklyn. Yeah. Oops. Keep going to read the rest of the sentence. How much the atmosphere absorbs. So the third and final is the amount of solar energy absorbed by the clouds. Why don't we add to that parentheses? Actually, I just said it. Amount absorbed by the atmosphere, but I really want you to say parentheses, clouds. So today, we're not getting nearly as much energy from the sun as we were yesterday. Because the energy is not going through the clouds.
What's the temperature right now?
I'm not sure.
What is that?
That is a thermometer.
It's not the temperature.
Yes, sir. What?
Oh, it's 70 or the? That's the hottest it's ever been here.
It is currently 70 degrees Fahrenheit with 48% humidity. All right, so since we were a little behind, maybe we'll get to that compare and contrast tomorrow. But since we just took the notes, actually, why don't you give, no, I lied. What's the word insolation mean? So I've already heard from Drake and Phoenix. No, I have Drake and Remy, sorry, Phoenix. And Remy. And I heard from Brooklyn. Somebody else tell me what insolation is. You got it?
Stuff in it.
No, I didn't say insulation. I said insolation. Go back to the reading. Remy, you already helped us out, so thank you, but I'm gonna wait for somebody else. Insolation. You find it? You think? It's not that difficult. I think it's even underlined, isn't it? Energy that reaches, or do you have another addition to that, Alex? Yes, so which is what you said too. You weren't wrong. But easier than what you said, Sienna, is insolation is incoming solar radiation, which is the energy reaching us from the sun, yes. Hopefully you can see where the heck they got the word insolation. Incoming solar radiation. So they took the the soul, and the ation from those three words and made up a brand new word. Incoming solar radiation is insolation. Not to be confused, I'm not pronouncing insolation incorrectly. Insolation is the pink stuff in your attic that helps keep the heat or the cold in. Insolation is just energy reaching us from the sun.
Some people do spray foam.
Spray foam is also insulation, correct? But again, not what we're talking about. Don't get those confused. So now, like I was saying, actually, let's just knock it out. What's a huge difference for external energy? Okay, let's add that bullet. External energy comes from the sun. Internal energy, give me a huge difference. Comes from the inside of the earth, or comes from earth. Doesn't have to be the inside, I guess. Another one. Big difference. Oh, hey, everyone, we just wrote these about 3 seconds ago. Maybe we'll save this part for homework. We'll come back to this. You can do this one on your own tonight then.
I got one.
Oh, you got one?
I got one for.
Oh, you got a difference for internal?
Yeah, block, wait, block, I don't want.
No, you got one next, Phoenix. What?
Radioactive.
Okay, so it comes from inside the earth in the form of radioactive decay. Phoenix, you got one, or you want to save it for your homework?
I got one
What is it?
for external.
External? Give me one.
Hold on. Actually, internal.
Okay,
Internal energy refers to the energy that comes from inside the earth.
yeah, we already got that. Give me another one.
There are two principal sources of Earth's internal heat energy.
Okay, what are they?
Some of the energy is left over from the formation of the planet about 4.6 billion years ago.
Okay, so some of it is from radioactive decay, and some is from the leftover from formation of Earth. Give me another major difference. Landon, Jenna, Allison. Who else has,
Can I go again?
no,
Clock your shot.
Olivia, I'm not sure if you got me one or not.
Thank you.
Drake's good. You got one for which one? External, what do you want to tell me about it?
Position of the sun in the sky.
Okay, so one thing that affects how much we get is how high the sun is in the sky. Give me another one. Hello, everyone else.
I got one.
Allison. Okay, how long the sun is out? How long sun is out? Jenna, you got the last one? Okay, so, how much is blocked by clouds? Anybody got a similarity? The heck is similar between these two?
They both back heat.
Okay, they're both have heat.
Excellent.
Which, if you remember from 8th grade, heat is energy. And that was a perfect transition into what we're going to do next. I don't know what grade you guys did it in, but it was either 6th, 7th, or 8th grade. I'm thinking it was 8th grade. You learned a lot about energy. Yeah. At least in the 8th grade science test, if you remember, if you took it, there was a ruler with a block of wood and you had to roll, what was it, a ball down the ruler and it hit a cup and it pushed the cup. No, but we learned about, when you did that, you were learning about the energy of motion and, which is kinetic energy, and you learned about potential energy, so stored up energy. You also learned about how heat can, or how energy can move from one thing to another. It's called energy transfer. Anybody remember some of the ways that heat can be moved from one object to another?
Batteries.
That would be storing energy. So you're not all completely off base. These are vocab words. I'm not sure if you're going to remember them. Conduction is one of them. There it is. That ringing any bells? So conduction is one way that heat moves from one object to another. There is another one. In fact, there's two more. Convection, that's the one we learned this year. Convection, if you remember, we have hot, in our case, we had the lava lamp, which I can no longer show you because I dropped it on the ground. But which stinks, by the way, makes a big mess. But convection, what happens with convection? How does heat move?
Cycle.
It's that cycle where warm molecules move up, cold molecules move down. There's one more. No, that's not energy transfer, but it's along the same lines. I see where you're going with it. It is radiation. Anybody know a type of radiation? Or where something that has radiation, where heat, X-rays are a type of radiation, you're not wrong. Also has some radioactive radiation that comes off of it. This is the one, what? Okay, so we're talking about energy and heat transfer though. So it sounds like that's the one we're a little sketchy on.
Microwave.
Microwave is a type of radiation, yep. Okay, do you have the 88.8 gigawatts, 88.6, 80? Anyway, while we think, you're right, it is 1.1.
We're talking about that.
And who do you have to be going, 88 miles an hour? Yeah, I knew that 88 was coming from somewhere. Who needs a highlighter? I forgot to put it on the board.
I have one.
I mean, so everybody needs a highlighter. Who needs me to deliver one?
Anyone.
Alex, you got one or you need a
I'm ready.
delivery?
No,
You ready for this?
Jake, can I have your shoe?
Oh, dude, I couldn't have even done that better.
You okay?
Oh, feeling got in the way.
What time?
Sorry. Oh, I totally denied you, but
There 12 running line grade.
you got one. You're good. Anybody else need delivery?
Either one time.
All right, so since we were talking about heat transfer, let's hit up page 7, please. Yeah, another reading. I am sorry that we kind of just wrapped up that last one and moved into this one. It's really because we were behind a little bit. But yeah, another reading, hence the reason you have highlighters. You also know that when I do a reading, what's on the next page? Questions. It's really the notes. It's not even the questions. Whoa, you can't see them on the board. So in the reading, we're not just blindly reading as always. We are reading for a purpose, and that purpose is first to identify the definition of all 3 types of energy transfer. So we're going to be looking for how does radiation move energy? How does conduction move energy? How does convection move energy? Then we're going to be talking about the phase of energy that the energy can move through. By the way, do you know what I mean when I say phase of matter? What are my choices? Yeah. So I'm looking here. Can the energy move through solids, liquids, or gases? And by the way, it could be more than one. An example, there's an example in the reading, but I'm also going to have you think of some examples, and then we'll obviously draw a cool picture to help us remember each one of these. So right now you got your highlighters. We're not writing at all yet. You're just highlighting these answers to this in the reading. So, are you ready?
Yeah.
Okay, thanks, Mr. B.
All right, let's start with radiation.
I gotta take attendance anyway.
All objects radiate energy and heat, even your own body. However, the radiation coming from outer objects is more intense than coming from cooler objects. Radiation leaves an object in the form of waves called electromagnetic waves. Electromagnetic waves travel through empty space. The hotter an object, the shorter the wavelength. As you stand in front of the campfire, holding your cold fingertips out in front of you, what do you feel? Slowly, your fingers begin to warm up as they absorb the radiation coming from the fire. The infrared waves, or heat rays, leave the hot fire and radiate outward towards your hands. All right, conduction. Conduction. Heat also can be transferred from one object to another, or from one molecule to another, the process of conduction. As one molecule is heated, it begins to move and shape rapidly. As it does so, it passes some of its heat energy to other molecules around it. Through this process, all the molecules of an object pass heat from one to another until they are all hot. During conduction, the objects are in direct contact with each other. Return to the example of a campfire. What happens if you use an old metal hanger to roast hot dogs? As the hot dog cooks, the fire heats the end of the hanger. If we leave the hanger in the fire long enough, eventually the end we are holding will become too hot for us to handle. This happened despite the fact that this end was never placed in the flames. Heat was transferred from the flames to the metal, and then from the molecule to molecule in the hanger via conduction until it reaches your sensitive fingers.
Guys, I know a hanger is a very weird example, but I totally a fork. I should have just said a long fork. I don't know why I went with a hanger.
Have you used the hanger?
I used a hanger. This must have been from a book and I just copied it, but
I
I
could get hanger with board. I'll get it.
like a metal hanger that you hang clothes on, like a skewer is what I meant. I should have just said a fork with a long handle is what I should have said. So picture fork with a long handle that you're sticking in a fire there.
We go do radiation.
No. Next.
Convection. The final way making is transferred from one place to another is convection. Convection takes place when heated molecules move from one place to another, taking the heat with them. Convection is common in both the atmosphere as well as the ocean. Convection happens to gases and liquids. Heated air in our atmosphere expands, becoming less dense. Because it is less dense, it rises upward. Cooler air rushes in to replace the air that left it up. As warm air rises, the cool air falls, a giant circular pattern is created. Eventually, the warmer air cools and begins to fall again. Convection also takes place within the sun. Vast amounts of hot gas rise up towards the surface of the sun. As they do so, they become cooler and begin to fall back down towards the center of the sun. As they do so, they again heat up, begin to rise again over and over again, rising and falling in seemingly eternal circular pattern.
Okay, so now that we've discussed the whole hanger versus fork situation, what do you got for these? How does energy get moved through radiation? Let's start. Yes, waves. Before we even start though, I noticed I don't have a title here. I know it's on the other page, but let's just add the title here. So this is heat, which is also just plain old energy transfer. And if you don't know what transfer means, make sure you know that that's move. Like, how does it get moved? So I'm gonna go exactly with what Drake said. I'm actually gonna simplify it a little bit more. So how does energy get transferred through radiation? Energy is moved in the form of waves. So I have a couple of clarifying questions. Do you have to touch the object to feel the heat coming off of an object in radiation? No, no touching. Next clarifying question. Does the actual thing that's heated up move to your hand? No. For example, I'm going to skip to the example. What was a good example for radiation transfer? No, this one wasn't the hanger. This one was the heat from a fire. Another one was the sun. Energy coming from the sun. Do we have to touch the sun to feel it? No. And here was my other clarifying question. Do pieces of the sun come down and touch us? No. So in this case, the hot stuff stays where it was. The sun stays where it was, and its energy gets to us in the form of waves. So no touching and no movement of those hot objects. So what phase of matter did they go through for radiation? Go back if you don't. This one was through air, or since we're scientists people now, we're going to say through gas. And we did have two examples. So heat from the sun, or even a fire. You don't have to touch the fire to feel the heat. Can you think of anything else that radiates heat where you can feel the heat from it without even touching it?
So,
A stove. So you could touch a stove, but do you have to touch the stove to feel the heat? No. Even like your battery chargers, they radiate heat. They put heat out into the environment without touching it. Even your phones, if you're on it long enough, they will heat up. Light bulbs, you do not have, now all these things, yes, you can touch them, but you don't have to. Ever run a mile and feel like you can feel the heat coming off your face? That you are radiating heat. So you are giving off heat. What should we draw for a picture? That could be one, so you could draw the sunshine. And I like if I draw the sunshine to show the waves coming off. And then of course, we're down here with a big old smile on our face when it's sunning. Oh, my big old smile is pretty sketchy. Yeah, okay, I'm not that good. You could, of course, draw a campfire and feel the heat coming off the campfire. Just make sure you see that you're not touching the campfire for radiation. So conduction, I heard a lot from Drake. I want to hear from all my other classmates here. How can we describe conduction? Okay, give me the description, because clearly hanger wasn't it. How does heat get moved through conduction?
Got it.
Okay, so this is when heat is moved when heat is moved when one hot molecule touches another molecule. So this time you have to touch it. So this says heat is moved when one hot molecule touches another molecule. So this time you gotta touch it. That's the first thing. Second thing, remember how I asked, does the hot molecule come from the sun and touch you when you feel it? And you said no. How about this? Let's picture the hanger or the fork in a fire. Oh, well, because I like campfires, dude.
Yeah.
Okay, let's talk about a pan on the stove. Yeah, ever burn yourself when you touch a hot handle on a pan? Okay, if you haven't, you don't cook enough. Just saying. Okay, so if your mom is still cooking you every meal, help her out. Help her out, dude. Or are you living with her forever also? Just saying. Help her out. Second, even if you made ramen, you could burn, or do you make it in the microwave? No, okay, I know, I did in college, had to make it in microwave, but anyway, you take that hot pan. If there's no protection on the handle, how's that feel when you touch it? Yeah, great, pretty hot. But how about this? Was the handle on the heating element?
No.
No. Why does the handle get hot then? If it's not on the fire, if it's not on the electric coil, if you have an electric stove. Because that heat goes from the hot molecule, so the fire does heat up the bottom of the pan, absolutely. But then that hot molecule touches the molecule next to it and warms up that molecule. Then that molecule touches the one next to it and warms that one up, all the way up the handle. So again, do the heated molecules go from the fire to the handle? They do not. They just touch each other and warm each other up. So the hot things are not actually moving again. So what type of matter do these go through? Solid and liquid. It might happen a little bit through gases, where one hot gas can touch another, but we'll save that as the radiation, because that's going to be more than moving in waves. Yeah. The example. Okay, the hanger. Are you going to say the hanger? Okay. Let's go. Trenton was really adamant that we just use a simpler one. So let's just use that pan. So I'm going to put my pan here. That's on a fire. It's going to have a handle. Oh, sorry. So, yes, you can write hot pan on stove. You could write fork in a fire. Anything else that you've ever touched and burned yourself? Okay. Mufflers. Mufflers are hot. Just had to take apart my dishwasher, that heating element in the dishwasher. If you touch it, it's hot. So there's lots of, anytime you're touching something and burning yourself, that's gonna be conduction. All right, here's the picture. So, let's have that fire. Here's you. Here's your hand and you're holding a fork in a fire. And you say, ow, and you're going to be sad. What?
Let's try everyone my drawing.
Maybe after we get all the way done, because we only have 10 minutes to finish up everything. Now convection. I don't care. Convection. What's this one?
Moving from one place to another.
Yes. So this one is when hot molecules move and take heat with them. Remember warm air rise? Remember our lava lamp? Was the hot lava actually moving in the lava lamp? Was the hot lava moving or did the hot lava stay still? Yeah, it moved, it went up. And then what happened to the cold lava? It went down. So this is different than radiation where the sun's not actually coming down and touching us. This case, the hot stuff is actually moving. The warm molecules are going up, the cold molecules are going down. What phase of matter does this happen in? It absolutely happens in gases. When we're talking about warm air rising, that's a gas. It absolutely happens in liquids because that's boiling water. Does it happen to solids ever? There's nothing solid that's moving around like in the earth. Yeah, we got some solids. No, but the solid layers of the earth, there is some solid parts that are rising. I know, we can cross off the solids if it's not making you feel comfortable, but it does happen inside the earth. What example do you want to use for this one? What example do you want to use for this one? Okay, we could use lava. What you wanted, everyone? Lava lamp. What about hot air balloon? Okay, because the heat, again, why does the hot air balloon go up? Because the molecules, the hot molecules are actually going up. Yep. So this one is different because the molecules are actually moving this time. Can you guys think of any other examples? Lava, oh yeah, you said that one. Even boiling water. Where do the bubbles go for that are the hot water? They go up. The bubbles when they're rising, that's the hot water go up. So that's the one I'm going to draw only because I can draw that picture. So there's my pot. Here's my fire. I'm going to draw that warm rising and the cold sinking. We're going to be coming back over and over again to these different types of movement of energy over the next couple of weeks. So these are all things that are going to have to be solidified for you to understand. Now I see you packing up, but we're not quite done. What do you got a question? What? Yeah, 1 second. Let me just make sure we know what's for homework. Homework's listed over there. So homework is pages 5 and 6. There are 16 Regents questions. These all have to do with the atmosphere reference table that we talked about yesterday on page 14. And that reference table on the front page that shows how much like oxygen and carbon and nitrogen are all in the atmosphere. So you're gonna use page 14 and page 1 to do your homework. And just a reminder, or maybe an announcement, if you did not turn in your take-home test, do it tonight. I will take 15% off, but I'm telling you an 85 is not a 0. So start yourself off at an 85 instead of just getting a flat out 0. So if you still owe the take-home test, get that in, okay? All right, Remy, you wanted to show us your picture.